we're going to talk about an example here. Saturated steam at 100 degrees Celsius. Okay, so the keyword here is saturated steam, and it is 100 degrees Celsius. It is heated to 400 degrees Celsius. Okay, now there is a system where actually 100 degrees Celsius heated to 400 degrees Celsius at 1 atm, which means that the atmosphere is constant. So determine the required heat input, okay, in terms of joule per second for a continuous stream flowing at 100 kilogram per second undergoes the process at constant pressure. And now, if 100 kilogram undergoes the process in a constant volume. So first of all, we need to identify, is this an open system or is it a closed system? So if you look closely into this particular problem, we are talking now about rate. So whenever that it involves any kind of rate, okay, and another keyword here is continuous, so this is an open system. Okay. Another one is actually they talk about 100 kilogram only. There is no rate involved here. Okay, and in terms of the process is in a constant volume, right? So this is what we call as closed system. So you can see the differentiation between the first problem and the second one is there is a rate here in the first problem, but there is no rate, just mass in the second problem. So let's have a look at the first example, okay, how we can solve this. So first of all, we need to draw actually the flow chart, right? So there is a system where, okay, so I would say this is like a heater, or it could be a furnace, where actually it heats up 100 degrees Celsius saturated. Now it becomes superheated, okay, superheated steam. So here you have 100 kilogram water vapor per second, and similarly you have also 100 kilogram water vapor per second, but there is a change of the temperature. So first step, we should properly draw and label flowchart is necessary, and if possible, determine flow rates of all stream component. So here the flow rate is already being determined, and we have start already to draw and label the flowchart. So what's next? The next thing is actually we need to determine specific enthalpies or specific internal energies. We know that this is problem related to open system, so we should know what will be the specific enthalpy of each stream component. So how to do that? Okay. So what we need to do is actually refer to the steam table. Before I discuss this slide, I'm going to bring you, okay, to actually finding the steam table. So let's have a look at the appendix that I have given you earlier. So if you refer to the ULearn that I have given to you, so there is what we call as appendices for energy balance. So what we can do is actually we want to look at the right table, okay, when we actually at the right table where we should refer, how we going to get the value for the enthalpy. So here this is table B1, selected physical property data, okay, which we're going to also use this in the future, but I'm going to bring you directly to table B. This is table B3, and then this is table B4, and I'm going to bring you to table B5. Okay, so for table B5, this is properties of saturated steam. Okay, saturated steam of temperature table. So when you given this problem, is that we need to look at the 100 kilogram of water vapor which is saturated 100 degrees Celsius. Okay, so when we look back at this problem, so we know that the temperature is it is a saturated steam and it is at 100 degrees Celsius. So we will go to 100 degrees Celsius. Okay, so you were given here the volume, the information such as what will be the specific volume, specific internal energy, as well as specific enthalpy. So specific enthalpy, this is what we call here as you have a water, evaporation, and steam. And now your water is not actually at the form of the liquid. The form of water itself is not in the liquid form. It is in the form of the steam form. So when you go to straight to 100 degree, then you know that the value is 2676. This is what we call as specific enthalpy. Okay, specific enthalpy of kilojoule per kilogram. So you're given this value 2676, right? So this is why actually in this slide you have the information that the inlet saturated steam at 100 degrees Celsius is 2676 kilojoule per kilogram. The second one is we talk about outlet steam at 400 degrees Celsius. So let's have a look here. Is there any value of 400 degrees Celsius? No, because the temperature for water only reach up to 102. So therefore, the steam itself must be saturated steam. So this is actually we call it as saturated steam. So the steam, because there is no temperature at 102, so the outlet stream must be a superheated steam. So we skip straight away because this is only table B6 for saturated steam as well. So we skip to table B7. So when we go to table B7, it is a properties of superheated steam here. This is what you're being told, superheated steam. Okay. So and then you were given a pressure initially. The pressure in the problem, okay, is given as at constant pressure, and the pressure is given at 1 atm. So at 1 atm, when we go back to the table, then we go and find a pressure of 1 atm, and then we need to find the specific enthalpy. Again, this is given as specific enthalpy, specific internal energy, and specific volume. So if you want to go the specific enthalpy for 400 degrees Celsius, so you have to look at the temperature up here. So there is no temperature for 400 degrees Celsius, so you bring it down. So let's go down. Okay, now you find temperature at 400 degrees Celsius and the pressure is at 1 bar. Okay, 1 atmospheric pressure, it is equivalent to 1 bar. Then you know that the H value, specific enthalpy, is 3278. So this is where actually, if you look at this problem, then you highlighted 3278 kilojoule per kilogram from table B7. Okay, so now you have already seen that from the previous slide. Okay, from the previous slide that you have actually looked at how you have be able to determine the H value, specific enthalpy, at 100 degrees Celsius for saturated steam, and the enthalpy value, specific enthalpy value for 400 degrees Celsius in table B7, which is considered as superheated steam.